Welcome to this video. So, who says that calculus cannot be fun? I'm going to show you a cat video, and I'll actually use that to introduce some mathematics. So let's see why we need this and why I'm going to do that. So here we are, and what I'm going to tell about is I'm going to show you a video of a cat, and in that video you should look at the pupils, so in the eye of the cat, because they change size. And then I'm going to use a bit of a more general formula that we can find where the size of the pupil depends on the light intensity. So when it's very dark, then the pupil opens up, and when it's very bright, then the pupil closes down. That's what generally happens for cats and also for human beings and other animals. And using that formula for the size of the pupil, we are going to look at limiting cases. So what happens if the light goes completely dark or it goes completely to the maximum? And that will bring us to the mathematical concept of limit. So I'm using cats and cat videos to tell you a little bit about the mathematical concept of limit. And that's what we'll be focusing on in a couple of future videos. So let's see, here we have the cat and the source is there. So this is a YouTube video. So look at the pupil size of the cat. So just focus on its eyes. And then you see that they become larger and smaller. So it's very, very small here, and then it goes bigger. Of course, the cat is really watching a video of itself here, but you see how the pupil size changes. So that's all I wanted to do, but hopefully this makes it a little bit more interesting for you. So let's see for a model of the pupil of an animal's eyes. And here, if you look at the numbers that are going to come out, this is not a cat anymore. This is a general animal, and the pupil depends on the intensity of the light. So what I have here is a formula. This formula gives the diameter of the animal's pupils as a function of the light intensity. So x is some measure of the light intensity. Very large values of x indicate that there is a lot of light. Very small values of x, close to 0, means that it goes dark. Now, the problem is, or what we're interested in to see is to find the diameter for minimum light. So what is minimum light? Well, it's x going to 0. And for maximum light, let me switch here. Okay, yeah, like that. And for maximum light, so that's x going to infinity. Now, if you look at this formula here, then you see that there is an x to the power minus 1/2 in there. So this thing here, and that is also in the denominator, it says x to the power minus 1/2. So that really is 1 over square root of x. So what you see is that I cannot simply plug in x equal to 0, because then I would have division by 0 and 1 over 0. That is not defined, so that doesn't work here. Now, if I would plot this function as a function of x, I've done that with some software. And what you see here is that for x very close to 0, it seems that this function is going to 40. What you also see is that if I pick larger and larger values of x, that the function keeps decreasing, and it seems to creep slowly towards a limiting value of, well, if you would zoom in, then you would find it to be 6 millimeters. Now, of course, in mathematics, we don't really like to say, well, just look at the graph and read off these values. We would actually like to compute them. So we need some new machinery on how to do that. So this is our function that we're interested in. This is the formula that was on the previous slide. And I rewrote it a little bit. So we have 160 over square root of x plus 90. And in the denominator, we have 4 over square root of x plus 15. Now, let's look at this formula. And let's try to determine f0, but f0, that doesn't exist. So I cannot really write that down because then I would have division by 0, and well, we don't want that. That's not defined. Also, we would like to know the value of x going to infinity, x becoming larger and larger. So how can we do that? So let's see. First, the case where we have minimum light. So I would like to take x closer and closer to 0, but not equal to 0. And this idea that we get values that are closer and closer to, in this case, 0, but it could also be any other number, but not equal to that dangerous number 0 here, that is the mathematical concept of limit. So in the boxed formula here, the limit of x tending to 0 of f of x. So that means that we take x closer and closer, but not equal to 0. Now, if we do that, then we can rewrite our formula. So here, what this means is that we take x close to 0, not equal to 0, and I can multiply both in the numerator and denominator with the square root of x. If x is a small positive number, I'm just multiplying with 1, and the formula doesn't change. So if you do the multiplication in the numerator, you find 160 plus 90 times square root of x. In the denominator, we get 4 plus 15 square root of x. And the interesting thing is that the new expression that we have here, well, that exists for x equals 0. So I can now simply plug in x equal to 0. And if you do that, then you find 160 over 4 is 40. So apparently, the pupil size for minimum light for x really going to 0 equals 40. And this is the correct mathematical way to write this down. So then we are not being bothered by the function not existing at 0. This is the way to circumvent that. So this notation with these limits here, that helps us exactly determine the limiting value for x going to 0. Similarly, so conclusion is that in minimum light, the pupils have diameter 40 millimeters. For maximum light, that is x going to infinity, that's what we write here. So the limit x going to infinity of fx. What we do there is we look at the formula, and 160 over square root of x. If x is going to infinity, square root of x is also going to infinity. Some number over infinity, that is 0. So in this situation, we get 90 over 15 is 6. So the conclusion is, in maximum light, the pupils will have diameter 6 millimeters. Okay. A bit more general, so this was based on an example. Another example is the function sine of x over x. And we will meet this function again as a kind of standard limit. But you see here that if you would plug in x equals 0, you would have 0 divided by 0, which is undefined. So we have division by 0. If you plot the graph of this function, this is what you get. And you see that it's actually quite smooth, close to 0. And if you pick numbers very close to 0 but unequal to 0, you see that these numbers get very close to 1. And indeed, if you just plug in numbers, so I did that here, so I evaluate the function at minus 1 over 10, minus 1 over 100, minus 1 over 1000, and you see indeed that these numbers go to 1. And the same if you would fill in positive numbers. So basically, whether you go to 0 from this direction or from that direction, that doesn't really matter. And that also makes sense, right? Because if you look here at this formula, you see that f of minus x, that's sine minus x over minus x, which is minus sine of x over minus x. And this is simply the same as f of x. So it doesn't come as a surprise that both on the left and the right we find the same values here. So these two examples are meant to prepare you for the concept of limits. So what we do in limits is that we are going to evaluate a function very close to some dangerous x value, but not equal to that. So as a summary, what we have found is how you can find the value of a function for the value of x near 0 but not equal to 0. So that is going to be super important in the next videos always. We get very close values to a, say, so x is going to a, and then x becomes very, very close to a but not equal to a, and here 0. You can also have limits for x going to infinity or minus infinity. And we have also seen a numerical experiment that shows you how you can numerically determine where the function goes to. So this was a short introductory video, and in the next couple of videos we will study limits, and we will use limits to go to the derivative of a function, so tangent lines to a function and the derivative of a function. But that's all for the future. This video ends here, and I hope to see you in the next one.